Hello, I'm Zixing Lei of Shanghai Jiaotong University. It's my great honor to share our work about collaborative perception on the realistic communication scenarios, especially latency. First of all, I will introduce collaborative perception, a rising research topic in the past 3 years. Single-agent perception suffered from occlusion and long-range issues for a long time. Therefore, the concept of collaborative perception came into being. As shown in the right figure, due to occlusion, the sensor based on the car itself cannot obtain the relevant information of this pedestrian. However, if the car can communicate with the roadside unit, the pedestrian behind the trunk can be found in time to ensure safety in this situation. In addition, for example, the collaborative situational awareness of UAV cluster can also play an important role in disaster relief. Now we will introduce the related work, SyncNet. It follows intermediate fusion architecture and introduces the knowledge distillation into the pipeline. SyncNet effectively improves detection performance. You may wonder why intermediate fusion. On the one hand, the transmission of raw sensing data will cause great pressure on the communication system. On the other hand, the transmission of perception results only, such as bounding box only, will lead to the lack of information for the post-error correction and the following detection task. Therefore, most works focus on the flexible and efficient intermediate feature fusion architecture. Besides, V2XC, the first public dataset in collaborative perception on autonomous driving, was proposed in RAL. Now let's introduce the motivation of work. In this latency insensitivity collaboration scenario, due to latency of communication and calculation, when two vehicles receive the collaboration data from each other, their positions keep changing. Based on the detection results of previous locations, it's likely to mislead the detection system. However, in the latency-aware system, since latency is a variable which is taken into our consideration, we can predict and correct vehicle position at current time according to the vehicle track in the history. Now let's take a look at our system overview. First, it's a detection model with communication capability. It can receive the collaborative features of other agents and save the historical features in the memory. A predictor module is used to compensate the features and weights of collaboration at current time. Therefore, we expand the original 4 steps framework of collaborative perception to include a latency compensation module. To achieve that, we leverage historical collaborative data to predict the features and weight at the current time. We use a dual-branch conv LSTM structure to compensate for the feature and weight of collaboration respectively. The input contains both features and weights. We hope that it can help compensation module to aware that the importance of each region is different and focus on the region with the higher importance. In addition, we designed a time modulation structure which can improve the performance under low latency conditions by further fusing the predicted features and the received asynchronous feature. We also designed the corresponding loss function, including detection loss, prediction loss of each collaborative features and fused features and weights. We hope that even if there are some errors in each single prediction, we can ensure that the fused feature can minimize the errors. Now let's take a look at the experimental results. The green line represents previous SOTA collaborative perception method, SyncNet. It has a lot of performance degradation in the latency scenario. After adding our compensation module, the performance is improved up to 15.6%. On the fusion structure of V2VNet and the straightforward transformer fusion module, the latency compensation module can also achieve a great performance improvement. The visualization results also show the performance of compensation. In the latency insensitivity scenarios, the detector gives the position of the two vehicles in the purple box 5 frames ago, while the model including latency compensation module predicted the actual position. Thank you for your listening, and we hope the computer vision community can pay more attention to the collaborative perception task and further improve the performance and robustness of perception. If you are interested in the robustness of collaborative perception, you can track following relevant work. Thanks.